Okay, so we've been discussing gates since yesterday, and I just wanted to correct one error that I made in the lecture yesterday. So I said how, so recall the statement that I made. Single qubit gates, I said, are essentially 2 cross 2 unitary matrices, right? And I said they belong to a group U2, right? And this is a group under multiplication. Now I said that this is equivalently, we could say that these unitary matrices belong to the special unitary group. And the special unitary group is basically the set of 2 cross 2 unitary matrices with determinant not plus minus 1, but it should just be 1. Okay, that's an error that I made in writing down the definition. Sometimes people do put the minus, but I think the correct definition is to not say it with the minus 1 and just say that these are unitary matrices with determinant u is 1. The general unitary matrix, as we discussed yesterday, has only phases as its eigenvalues are all pure phase, right? So its determinant, the modulus of the determinant is 1 for a general unitary matrix, right? But I had said that without loss of generality, we can say that we can often let our single qubit unitaries be elements of the special unitary group by essentially adding an overall phase to the gains, right? So for example, think of your sigma z, or rather, let's say I convert to z, right? So think of z, right? Now this, of course, has determinant -1, right? So what do? We can think of iz, right? Iz is the gate I00 minus I, right? And this, of course, has determinant +1, and this belongs to SU2, right? Just wanted to clarify this. But now, how do we argue that I can, without loss of generality, talk about IZ instead of Z? Because the gate action is the same, right? Yes, so when I input an arbitrary superposition of the form alpha 0 plus beta 1, and the gate that I have is the IZ gate instead of the Z gate, what is the output? What is the output?
I times alpha get 0 minus beta get 1.
Exactly. So this is just an overall phase, right? And we said all states are equivalent up to an overall phase, so this doesn't matter, right? So essentially, we have gotten the desired output as the Z gate, right? And that's why, without loss of generality, I can say that this is the same as just a Z gate whose action is alpha 0 minus beta 1, right? So I hope this is clear. And yeah, I probably should not have said the plus minus one. I should have just said 1, right? And one can indeed make, without loss of generality, all our quantum gates to be elements of SU2 rather than U2. Okay? All right. Let's proceed now. We were discussing the rotation gates, right? So we were looking at the rotation gates. Of course, single qubit. And these are basically these kind of operators: minus theta by 2x, minus theta I theta by 2y, and minus I theta by 2z. And then we noted, was there a question? Okay. So, and then we noted that these are rotation gates because they each correspond to a rotation by angle theta, and that's why the argument here is theta. So, these gates correspond to a rotation by theta about the x, y, and z axis, the block sphere representation.
Ma'am,
Yeah.
so in that case of this rotation, does the
Yeah.
direction of rotation is important? I mean,
Yeah. Well, so actually for us, it's only the final state that matters, right?
hmm,
So, well, it is important to the extent that it's going to lead you to a different state, right? But this half angle correspondence, I think, makes sure that uh, you are not going to end up with a different state, but I'll have to check that statement. That's a good point. But I think this minus sign out here fixes the direction essentially, right? And yeah, so for example, with the Z rotation, we saw that it basically takes alpha. So I had said that it takes psi, which is cos alpha by 2, 0, plus e to the I phi sine alpha by 2, 1, to cos alpha by 2, 0, plus e to the I eta plus pi. Sine alpha by 2, 1. So if I were to visualize this in the block sphere, then I have a state which is making this alpha angle here, right? This is my sphere. This is the z-axis. So this angle out here is what is phi, right? So now what is the sense of the rotation?
uh, anti-clockwise, I mean, from X to Y.
Correct. It's counterclockwise. So it's like this, right? So the action of this Rz of theta is to rotate like this by theta. So you actually end up with a state, bigger sphere now, which while at the same angle alpha with the z axis, now has a projection which is gone as phi plus theta. If you were to flip this sign, in the sense if you were to make it minus, then you will realize that you will end up with a different state. So if it were to rotate the other way around, then you're going to end up with in a different region of the block sphere, right? So yeah, in that sense, it is important because, I mean, for us, it's not so much the sequence of steps that leads you, but it's a final state, right, that matters. And the final state is going to be different. So yeah, I mean, it's a reference, right? So I could have started by defining these gates with a plus sign and so on, but this is the standard convention. And in physics, this is also the way we represent the generators of rotation, right? So when I write e to the minus theta by 2x, the sigma x matrix is a generator of rotations about the x-axis, right? So that also fixes the sign for you here. Okay.
So that means this rotation direction matters.
Yes. Yes.
The final state point of view.
Yeah. Yeah.
Okay.
Yeah. See, the action of the same gate could be decomposed in different ways. Okay. And in fact, we will see some statements like that. So that's what I mean by saying that the sequence of exact sequence does not matter so much as what the final state is, right? And Rz of minus theta is going to lead me to a different state than Rz of theta. So then, of course, it matters, right? Okay, so now the next thing is to show that any single qubit gate can be decomposed in terms of a sequence of rotation gates, right? So there are several ways, like I said, of decomposing gates. So maybe I just call this as decomposing single qubit gates as sequences. When I say a sequence in the practical sense or in the circuit sense, the matrix, in the matrix sense, this is a product, right? So products of rotation gates. Now, I don't know if you recall, those of you who've done a course in classical dynamics of some form, I don't know if you recall your rigid body, rigid body motion ideas, but you would have studied that it is sufficient to specify the transformation of a rigid body using, you need basically two perpendicular axes, right? To fix two perpendicular axes, and in terms of that, you can describe transformation using these three angles, right? So that's exactly what is happening here as well, because, well, the underlying algebra is the same, right? The underlying algebra that governs your rigid body transformations and this is essentially the same. So that's why I said you can think of these XYZ as generators of rotations in the physics sense, right? In the physical sense. Okay, so the two axes that we will choose now are Z and Y. Okay. If you go through chapter 4 of Nielsen Chuang, you will find equivalent statements with respect to X and Y, and you can also make an equivalent statement with respect to X and Z. Okay. So what I'm going to just talk about is the simplest case essentially, which is the so-called ZY decomposition of a single qubit. So the statement is given any U, let's say belonging to SU2, then there exist alpha, beta, gamma, delta, that's 4 angles, okay? But we'll see that one of them is simply an overall phase, all real, okay? Such that U can be described as this overall phase e to the I alpha times a rotation by beta about the Z times a rotation by gamma about the Y times a rotation by delta about the Z. Of course, when I write it like this, in a circuit representation, how will this appear? So how do I represent this as a circuit? So I want to say U is the same as some sequence of boxes. What is the first box?
RZ. Yeah. RZ of delta. Sorry.
Or RZ of delta?
RZ of delta.
So this is what you guys have to keep in mind when you go from a matrix statement to a circuit. This is the gate that acts first. This is the gate that acts second. And this is the third. And the overall phase we have decided doesn't matter, right? Okay, so let me write down this circuit form correctly. So you have U can be realized as this sequence of gates, which is first RZ of delta followed by Ry of gamma followed by Rz of beta. Okay, so the action on any state is the same up to this overall e to the I alpha. So I could put this e to the I alpha if you wish here. But yeah, this is the statement, right? And since this is easy enough to prove, and this also helps us understand a little bit why these kind of statements hold. Let's try to prove this statement. Okay. So the proof simply has to do with how 2 cross 2 unitary can be written down. Okay. So if I were to write down in the standard computational basis, right, you know that so basically it starts by writing down the rows and columns of this matrix in the standard computational basis. So what do you know about the rows and columns of a unitary?
They are orthonormal.
Exactly. So the rows and columns of a unitary matrix, I should have listed this among the properties that we discussed yesterday, are orthonormal. Does everybody know this? Do you want me to explain this? So this comes again from the fact that U dagger U is identity. You write down the matrix form of this, right? So this will tell you that sum over I, let me say sum over J. So U dagger Ij, Ujk is delta Ik, right? So this in turn means that U star Ji, Ujk is delta Ik, where these are the elements of the matrix, right? The little u represents the corresponding matrix element, right? So you can use this to essentially show that for every such ik, right? So these are basically summing over the rows and columns, right? And you can use this to show that the rows and columns, if I were to take this unitary matrix, then think of these column vectors. These column vectors are mutually orthogonal. What is more, each of them by themselves, if I were to take the modulus squared of the elements, then it sums to 1, right? Those of you who are familiar with classical bistochastic matrices will find this property to be the same, right? That if you sum over the modulus squared of these entries, that must sum to 1, right? Of each column, similarly for each row. And if I take any two columns and take the inner product, if I take this column vector and this column vector and I take its inner product, that must vanish, right? So different column vectors are mutually orthogonal and each column vector is normalized, right? So this forms a set of orthonormal vectors. This forms a set of orthonormal vectors. So when I have a 2 cross 2 matrix, then it becomes easy for me to parameterize the entries of the matrix, right? Okay, so keep this in mind. This is where this property comes from. Now, so let me say that this 2 cross 2 matrix U, so let me say that it's either row or column, whichever way you want to think about it. I can think about it as two column vectors, which I call U1 and U1 perpendicular, okay? So in the standard basis, we can write this ket U1. So this is ket U1 for me. This is the first column. This is the second column. The second column has to be something which is perpendicular to the first column if it is to be a unitary matrix, right? So this is basically a normalized vector, and we very well know how to write normalized vectors in the 0, 1 basis. That's what we do all the time, right? So let me write this now as cos gamma by 2, 0 plus some phase, right? And I'll come to the phase, sine gamma by 2 1. Okay. Now this phase, for some reason, I want to write it as and well, you can separate it out as an overall phase and a relative phase and so on. So let me for now write it as e to the I lambda 1. Okay. e to the I lambda 1 minus lambda 2, where lambda 1 and lambda 2 are both some angles between 0 and pi, right? Sine gamma by 2, 1. And let me explicitly put a phase here as well as e to the minus I lambda 1 plus lambda 2. So I'm just putting two phases here, right? So I could have called this some phi 1 and phi 2, but I'm just breaking it up as some lambda 1 plus lambda 2 and lambda 1 minus lambda 2. Okay, it's just more convenient to write it this way. And then u1 perpendicular pretty much follows, because I have to write down a vector that is perpendicular to this, right? So basically, you see, I can pull out one of these out, right? If I want to make this an overall phase. So I can pull e to the minus I lambda 1 plus lambda 2 out, and then what remains inside is a plus 2 lambda 1, right? The lambda 2 part goes away. So essentially, what is an overall phase and a relative phase? I'm writing it out in this form as a lambda 1 plus lambda 2 and a lambda 1 minus lambda 2. Okay. Now, what does the second vector look like? The second column of the unitary matrix. It is something perpendicular to this, which means that should have an inner product that vanishes, right? So I claim that this is how I should write it. I should write it as sine gamma by 2 cos gamma by 2 here, right? But this should come with a minus to the basically minus of basically put minus of this phase here. So that's going to be minus I lambda 1 minus lambda 2 plus the negative of this phase. So that is plus lambda 1 plus lambda 2 cos gamma by 2, 1. Okay. So notice that this phase comes here with a negative sign. This phase comes here with a negative sign. Is this clear? Suppose you should check that u1 perpendicular u1 inner product is indeed 0, which is the same as u1 1 perpendicular. Okay. And of course, make sure that the inner product of each vector with itself is 1, normalized. So this is a pair of orthonormal vectors, and this is the most general way actually of writing down a pair of orthonormal vectors. If you, in the qubit case, we had a simpler form because of the fact that we could neglect this overall phase. But now we want to keep track of this, so we are writing it out in terms of essentially 3 real parameters, right? So if you think about it, there are 3 real parameters here. There's the gamma, which takes care of the amplitude, and as before, it comes with a cosine and a sine because the norm of the vector is 1. And then there is a lambda 1 and lambda 2, which take care of the phase. It's just that, like I said, instead of writing one phase here and one phase here, I'm writing them as a sum and difference. Okay. All right. So now, when you write this out as a matrix, then you already see this form emerging. And like I said, this is the simplest decomposition, because if you recall the form of the rotation matrix about y-axis, you will see that we are already there. Like you already have the form of the y rotation. Okay. So let's say u is now e to the minus I lambda 1 plus lambda 2 cos gamma by 2. So I'm just writing it out as a matrix now. Okay. And then e to the I lambda 1 minus lambda 2 sine, oh, oops, sorry. This should come here. Sorry. This comes with a minus sign and a minus sign here, right? And this is a minus sign here. Okay. And now it's easy to get this form. So can you already recognize? So I've already used gamma, right? So we already have the Ry of gamma structure, because recall that what is Ry of gamma? E to the minus I gamma by 2y. Remember, we said this is nothing but cos gamma by 2i minus I sine gamma by 2y, right? Yes. So in fact, you see, it's the IY term that shows up here when you write this as generators of rotations. That's because it's the IY, which is the element of the SU2. The Y alone is simply the element of U2. Okay, for those of you who are keeping track of the group action and so on. Okay, so what matrix is this? Yes, you just read off the entries of this matrix. So this is exactly cos gamma by 2 minus sine gamma by 2 sine gamma by 2. And you see this form is already here, right? Cos minus sine, sine cos. So now what's the final step to show that you can decompose as a sequence of Z and Y rotations? What remains to be done? What is the Z rotation matrix? Again, it will be cos delta by 2i minus I sine delta by 2z. So you can see that this is nothing but e to the plus minus I delta by 2 in the diagonals. I think this is what. Yes. So that's it, right? So we have this form already here. Simply, if you just follows from the fact that the columns and rows must be orthonormal, right? So in fact, all that you need to do now is set lambda 1 to be, I think, beta, and lambda 2 to be delta, and then you have it, right? So you need it to be beta by 2 and lambda 2 to be delta by 2. So then this U matrix. So if lambda 1 is beta by 2, you can just so the claim is that U is simply this now. Up to some overall phase. So I hope you can see this from here. Do you want me to write down a couple of more steps? Then I can do that. So if you want, we can reverse engineer this. So note that. So let's forget this overall phase for now. It's something we can make. Doesn't matter, as we said. So what we actually have is something like this, right? We have minus I beta by 2 delta by 2 cos gamma by 2. I minus beta by 2 plus delta by 2. Actually, it comes with a minus. Yeah, there's a plus delta by 2, and this one will have a minus. So this is correct. And then there's an overall minus sign. this comes with a minus plus beta by 2 minus delta by 2, and this comes with a plus, right? These two terms are both plus. Yeah, so to go from here to here shouldn't be too hard, right? So that pretty much proves this statement. And it's like I said, all that you needed to do was to write down the unitary matrix explicitly in some basis, right? So is this clear? Do you need me to work this out in further detail? So if not, I'm going to declare QED, okay? Because it's just matrix multiplication now. You just have to see for yourself that this essentially the beta by 2 part comes from multiplying with a diagonal matrix on this side with which simply has phases I beta by 2 plus minus I beta by 2, and the delta by 2 phase comes from multiplying on the other side with another diagonal matrix with phases plus minus delta by 2. Okay, and now you also understand why I parameterize the matrix in this very weird way by putting in a lambda 1 plus lambda 2 and a lambda 1 minus lambda 2. Instead of saying e to the I lambda 1 cos gamma by 2, e to the I lambda 2 sine gamma by 2, which also I could have done. Okay, the reason I did this was to get this product of two z rotations on either side to get that structure, right? And so the lambda 1 is basically the rotation angle beta, or rather half of the rotation angle on the left, and the lambda 2 is the rotation angle delta on the right. Okay. Okay, so like I said, this is just one parameterization. Okay. Equally, one could do. So is this clear? No questions? Okay, so equally, any unitary belonging to this SU2 can also be decomposed as a sequence of XY rotations and a sequence of YZ is what we did, XZ rotations, right? At least one of these statements I think is proved in Nelson Chuang, but we will, I mean, we don't have to go over this. I mean, I'll skip these proofs, okay? Because I think it suffices to show the principle of it, that it's possible to decompose these. And always what will come in is you will have these four real parameters, alpha, beta, gamma, delta, which are all typically angles between 0 and pi, or rather 0 and 2 pi. Actually, it depends. Okay, so that's why we don't say in general that they're all. So in this particular case, for example, you see that the gamma belongs to 0 to pi, but your beta, delta, and alpha can belong to 0 to 2 pi, right? So in general, they are reals of this form, right? So let me just say that in general, you will need these four real parameters, alpha, beta, gamma, delta, all of them reals. Okay. Now, as an aside, you can note that indeed, this is exactly the number of reals you need to parameterize any 2 cross 2 unitary matrix. Okay. So as an aside, please note that this is indeed the number of real parameters needed to specify let me say an element of SU2. Okay. Again, I'm not going to get into the details of that statement. Those of you interested, I'm sure, can figure this out yourself. You just have to write down the constraints and you will see how many real parameters you need. So it's just nice that you can now these real parameters have a very physical meaning in terms of rotations about the different axes of the block sphere. And this is, like I said, a very convenient way to decompose any quantum gate in terms of a sequence of rotations. And this is indeed how architectures like IBM Q use this to implement arbitrary gates. Okay, so this was all about single qubit gates, right? Now, what about multi-qubit gates, right? And as I said towards the end of yesterday's lecture, that if I want to work out a universal set of quantum gates, which means that there is some finite basic set of gates in terms of which all quantum gates can be decomposed, right? If this must be true, then I must have the ability to also do multi-qubit gates, right? This requires now when it comes to multi-qubit gates, so let's just look at the case of 2-qubit gates. Now we have seen 2-qubit gates before, right? Which is a 2-qubit gate that we've already seen?
C naught.
Yeah, so we have seen the C naught and we know what it looks like, we know what the matrix looks like, etc. So let's start with the C naught, okay? This is a circuit representation and you know what it does. So if I have X and a Y, it does nothing to the control. So this is called the control and this is called the target, and it flips the target if the control is set to 1. So in matrix form, we know that this takes, so let's look at the action on the standard basis. Now remember, this is the standard basis for 2 qubits, right? It's the standard product basis for 2 qubits. And what do you mean by product basis? It means that each of these states is a tensor product like this, right? Okay. 1 0 goes to, I'm writing it out in different ways. Huh? 1 0 goes to 1 1 and 1 1 goes to 1 0. What is the matrix corresponding to this? I'm not sure whether I wrote out this matrix earlier. So this is of course going to be a 4 cross 4 matrix, right? It's a gate acting on 2 qubit registers. So can someone read out the matrix elements of this for me?
And the first block diagonal will be an identity, first 2 cross 2.
Hmm.
The next block diagonal means the next will be a set of 2 cross 2 zeros.
Hmm.
And the other end of the diagonal will be a X gate.
Right. And then
And the remaining part
very
will
good.
be 0.
Yeah. Yeah, very good. This is indeed the way to visualize this in a block form, right? So what Amog was just telling us was a way to look at the C naught in this block form, where you essentially have the off diagonals to be 0, the full 0 matrices, and the diagonal it essentially has 2 diagonal blocks, one which is the identity matrix and the other which is the X matrix. So now I get a question whether the C naught, is it the same as the 2-qubit gate identity tensor X? Now that we know the Kronecker product, we know how to take this tensor product of matrices and all that. Can you answer this question for me? So in the circuit form, what I'm asking, yes, someone already has an answer. Yes, what's the answer? Yes or no?
No, ma'am.
Why not?
I mean, due to the definition of the tensor product, in case of the top one in I will have 0, 1, 0 in place of this identity.
Very good, exactly. So what you're saying is this matrix has a very different block structure, right? Where what happens? This now looks like this. Is this what you were saying, Nilesh?
Yes, ma'am.
Okay, so this block has this, and now, yeah. Okay, so there are two X blocks here, right? In this identity tensor X in this form, right? And this gate has this form, right? So where there's an identity here and there's an X here, right? Now this is a very important statement actually, that the C0 is doing a controlled X operation, but it is obviously not decomposable as identity on one qubit and X on the other qubit, right? So this is not true. Okay, this equality does not hold, right? So the C0, it is indeed a control X gate, and this is the notation that people often use. I don't know if it's used very much in the current literature, but in the, when I say current and earlier, it's just 10 years apart. 10 years ago, in most papers, you will find this notation being used, lambda of X, right? Lambda of X means a controlled X operation, right? So it is very much a controlled X operation, but it is not identity tensor X. And I hope you can convince yourself that neither is it X tensor identity, okay? Neither is it X tensor X or any such tensor product decomposition. In fact, the C0 does not have a tensor product decomposition. Into a product of, again, I'm going to use this word, local gates. Okay, so I can essentially classify my 2-qubit gates, the set of 2-qubit gates, into the local, and this is of course true for higher multi-qubits also, but 2-qubits is much easy to understand, into so-called non-local and local gates. Another way to think about this is entangling versus product gates. So the local gates are those which can simply be realized as tensor products like this, etc., right? And in a circuit form, they will simply look like this: X on one qubit, Z on the other qubit, or Hadamard on one qubit, S gate on another qubit, etc., right? So these are all products of local gates. By local, I mean that these gates are single qubit gates acting on individual qubits, right? So these are all decomposable gates, product gates. So I hope in your mind now you're seeing the kind of seeing the correspondence between product states and entangled states versus product gates and entangled gates, right? The non-local gates are gates like the C0, okay, which cannot be decomposed. By its very definition, what happens to the second qubit relies on the state of the first qubit because there is a control qubit and there is a target qubit, right? And the C0 is just one example of a controlled gate. There are several such controlled gates that one could consider. For example, you can now think of a CZ gate. The CZ is a controlled Z gate. So what does it do? Just like how the C0 would flip the second qubit if the control was set to 1, this will apply a Z gate to the target if the control is set to 1, right? So what would be the output of this? The 0, 0 will remain 0, 0, and the 0, 1 will remain 0, 1. But the 1, 0 again will remain a 1, 0, and the 1, 1 becomes a -1. So in general, you can think about applying a general controlled U. The notation for this is of the form lambda of U, okay? That's a symbol that people use typically. And by default, we assume that the first qubit is the control, the second qubit is the target, and controlled on the state of the first qubit. So the C is the control and T is the target. Controlled on the state of the first qubit, the second qubit undergoes an action of the unitary U. Okay, so we'll look into a little bit, we'll sort of go into a little bit more detail with these controlled unitaries on Monday. And then finally, I want to talk about the role of measurement in quantum circuits, right? And with that, I think that pretty much captures the syllabus of your mid-sem exam as well, right? Yeah, so we'll continue on Monday. Any questions? So because of the fact that we have these two classes of unitaries, local and non-local, surely in order to have a universal gate set, one must have a non-local unitary, right? So the universal set, therefore, must have a gate like the C0 or the control Z, right? Or any control unitary, because this class of unitaries cannot be decomposed as some local V tensor sum W, right? So, but of course, this is what I will show you on Monday. You can indeed map between such non-local gates. You can use local gates to go from C0 to control Z and vice versa. Okay, so that's why the universal set should always have one non-local gate and a bunch of single qubit gates. Okay, so let me stop here. I see there's a comment on chat that yes, indeed, entangling gates can never be decomposed as products of tensor product of single qubit gates. Okay. Okay, so let me stop sharing and I'll see you all on Monday. Was there a question?
Yes, ma'am. Ma'am,
Yeah.
the unitary vectors which we saw U1 and U2, they just
Yeah.
look like the states of an like spin operator along the n cap direction. Means n cap given by.
Exactly. Yeah, indeed, they are arbitrary single qubit states, no? Because it's like, what are the column vectors of a 2x2 unitary? They have to be normalized vectors, right? And the two columns should be mutually orthogonal. So indeed, it's basically like going to an arbitrary single qubit basis. It's as if you started from 0, 1, right?
Hmm.
And then you move to a different basis which has vectors u1 and u1 perpendicular. Let me share again. Yeah, indeed, that's a good way to think about it. See,
So, ma'am, what my question was that uh, this will be like implementing this would be just like passing a beam through a Stern-Gerlach experiment oriented along the proper direction. So the outcoming silver atoms will already be in the states U1 or U2. And since
well,
U1 and U2 can be any state, we can actually get any state from the state 0 or 1.
well, you shouldn't say Stern-Gerlach because the Stern-Gerlach on a single spin will only take you to. Indeed, you're right, right? I can design a Stern-Gerlach experiment with these two states, right? Um, to pick one of these two states. But like I said, the Stern-Gerlach on a single spin is going to pick one of these two states. A better analogy would be something like an optical element which will rotate your polarization like a wave plate, right? You're aware of
Yes.
what a half wave and a quarter wave plate and
Yes.
so on is?
Yes, ma'am. Yes.
Yeah, exactly. So this, I mean, like I said, the same math goes through for the polarization states, right?
Hmm.
So if you think of these as 0 and 1 as horizontal and vertical polarized, you can indeed achieve these unitaries by taking these kind of linear optical components like quarter wave plates and half wave plates, and then you can achieve arbitrary polarization direction, right?
Okay, so we don't use the Stern-Gerlach because it won't like give our intended state 100% of times.
Correct.
Is
The
that
Stern-Gerlach is more like a measurement, no? Because it's going to see if you take an ensemble, yes, but the unitary action you want it to hold on any single qubit state, no? On any ket0, ket1, if I want to realize this u, it should have this action on a single qubit state. If I send an ensemble through a Stern-Gerlach, eventually some fraction of them will land up there and some fraction will land up here. But if a single Stern-Gerlach will project you onto either U1 or U1 perp. It won't achieve this rotation. It will achieve a measurement in this basis. Is that
okay.
clear? Is the difference clear? Yeah. So if you want to do this, talk about this with spins, what you need is actually some electromagnetic pulses. So this is like rotating. So on the Bloch sphere, this is like saying that I start with 0, 1 and ket u is somewhere here, right? And ket u perp will be somewhere here, right? So it's basically a pulse which has to rotate me from, say, the z-axis to here. And so obviously it'll rotate the one state here. Okay?
Yes, ma'am.
Yeah,
Now I
so
get
this
it.
is, yeah. Is the idea clear?
So, hmm. So okay, we want to do this for all the states, so this won't work like measurement because it will
Measurement,
map all
yeah.
the states to the same state, but we want all means the state to get mapped to a rotated version of itself. So
The Stern-Gerlach setup is a probabilistic setup. It will collapse you to either. So if I do a Stern-Gerlach, with, let's say the orientation is now along this u perp, then some states will get mapped to ket u, collapse to ket u. Some states will collapse to u perp. If I send a beam of zeros, right, then it's not clear that every zero is going to get rotated to u and every one is going to get rotated to u plus. I mean u perp. Right. It is probabilistically going to throw me to one or the other. Because you can reverse this superposition. No? So the 0 will be some superposition of u1 and u1 perp. The 1 will be a superposition of u1 and u1 perpendicular. Right? So the Stern-Gerlach setup will probabilistically throw me into one or the other. It's a measurement.
yes, ma'am. Okay. Yes. Thank you.
Sure. So I guess I can stop recording.